Clocks tick differently in Boulder, Colorado.
Hi, I'm Jun Ye. I'm a physicist who built atomic clocks.
The most precise ones in the world.
Time is not what it seems to be.
He's fascinated by the measurement of time and by nature's influence on time.
Wow. Look at the rainbow, Andy. That's where you can draw inspiration. That's actually purple. That's actually quite rare to see that purple one in the inner side. This is made by nature. In the lab, we can make a laser. Beautiful colors just like that.
Einstein showed us that space and time are closely intertwined. At JILA at Boulder University, the focus is on the enigma of time.
Suppose I have a watch on my wrist, and I raise my arm by 1 centimeter. The time will speed up a little bit because you're going away from the Earth. You will see time change of 1 part in 10 to the 18th.
The slightest differences in height lead to measurable differences in time. At the end of our lives, our head is older than our feet.
I always feel building clocks, in some sense, is trying to ask nature how precise human beings can build scientific instruments to answer questions that are still eluding us. You bring together many quantum particles together, teach them how to dance, teach them how to do teamwork.
Ye's atomic clock is extremely stable, deviating less than a second in billions of years. Absolutely unbelievable.
This bright blue blob in our system are a few million strontium-87 atoms kind of suspended in the middle of a vacuum chamber purely by lasers.
These atoms are the equivalent of the pendulum on a grandfather clock. To minimize disturbance, they're cooled down to temperatures close to absolute zero.
So what we do is so-called laser cooling and trapping. You turn on certain colors of lasers, they're tuned to the right frequency where the atom can absorb photons and they get a recoil back. And if you repeatedly do this process, you can actually slow down atoms so that they can be cooled from they're moving with hundreds of meters per second, like a bullet trains randomly moving around, to something which is basically stand still.
All these blue and red lasers you can see at the moment are actually being used for cooling the atoms to maybe tens to hundreds of a millionth of a degree Celsius above the absolute zero.
The atoms are held by an optical lattice, a network of laser beams. This makes it possible to measure thousands of atoms at the same time.
With that, you can send in laser light acting as tweezers. But if we do that over 3 different directions, you can form a 3-dimensional optical lattice. And atoms, if you have them extremely cold with very orderly distributions, you can drop 1 atom per lattice site, almost like eggs distributed in an egg carton. With that all being done, the atom is waiting in the dark, waiting for you. You shine laser on, prepare the superposition, and the pendulum starts to swing. It's swinging 10 billion million cycles per second, so very fast swinging.
Strontium atoms acting like a pendulum. Time is measured based on this regular ticking.
You can start the pendulum swinging, and you can look back and say, how many swings have you done? And that means you have to make a laser to have a very, very high frequency phase stability. So all these are important ingredients to make optical atomic clock what it is today. What is amazing is that all the students are coming out of this, pushing the next frontier of quantum metrology, building best clocks, are the ones who go out there and become their own professors to teach the next generation students.
Jun has a huge passion for physics. I think it's very obvious in everything he does.
Yeah.
And it's kind of infectious as well, I would say.
You can get an email later tonight sometimes.
I've been thinking about your experiment. I also feel like Jun is kind of an artist as well, or kind of a poet. As a lot of times in group meetings, he'll speak in metaphors or compare, our journey of being a physicist to like climbing up mountains like over there. And yeah, it's kind of funny.
Yeah. Sometimes he thinks too fast. It's harder for me to catch up, but I feel it's my problem, not his.
There's a compelling evidence from astrophysical observations there's a dark matter in existence, and we don't know how they will interact with ordinary matter and ordinary field. So by building the most precise instrument that we can, they will allow you to explore these kind of deep connections.
Precise atomic clocks can help us investigate phenomena that, up until now, we've not been able to measure.
This is Andy. I take him for a walk all the time. Just Andy and myself walk in the late night and think about problems. Are you a good boy? Yes.
Ye's atomic clock can also measure changes in the Earth's gravitational field.
This is the beginning of the Rocky Mountain. And you can think of the mountain has a large mass. In principle, when the clock is precise enough, you'll be able to sense the presence of the mountain. And as we know, mass can bend the space. It can change time. Light is a carrier of information. It's a channel for us to communicate with nature. Through light, we know how atoms are built off. We know how molecules are vibrating, dancing. We can put many atoms together and ask what time it is. Through light, we can build, in the future, quantum computers that we can process information in a way that's much more powerful than the current computing platform.
And if he had an infinite amount of time?
I really would like to push the experimental precision, the measurement science, to such a frontier where gravity and quantum science can really make a meaningful connection for us. I just want to see how deterministic description of the world and the indeterministic description of quantum science, how do they meet? And how do we solve the problems of, is time always continuous?